Okay guys, so we're now getting into some of my favorite stuff, where we go into really high energy technologies, stuff that really hasn't been done before, but maybe we could use one day to reach other stars. Here we're gonna look at nuclear fusion and how we can use this inside of rocket engines. As we saw in the previous lecture, in a nutshell, nuclear fusion consists in taking four very light atoms of hydrogen and pushing them together at such high pressures and high temperatures where they vibrate extremely violently that they fuse together to give helium. And doing so, they generate a lot of extra energy. Aside from reacting antimatter with matter, is probably one of the methods we have of extracting the most energy from actual matter. So let's first have a look at how we can use nuclear fusion in a steady-state propulsion rocket system. So steady-state propulsion means that instead of having a single boom like a cannon that would propel the rocket, suddenly we have a system that's more continuous, like the reaction engines of airplanes. Theoretically, the way it would work is that the combustion chamber of such an engine would essentially be a magnetic bottle that confines at very high pressure atoms of deuterium and tritium, which are lighter than helium but heavier than hydrogen. By confining them at such high pressures and high temperatures through its magnetic field, the atoms of deuterium and tritium would fuse, releasing enormous amounts of energy and then being ejected from the chamber, therefore creating thrust like in a normal rocket. This system would need very high power electrical stimulation to be ignited. And that's because the temperature for safe sustaining fusion, so fusion that keeps going on without needing to be constantly ignited, is about 10 million degrees Kelvin. So this system has a potentially very high specific impulse because, as we saw before, specific impulse depends directly on the temperature inside the combustion chamber. And by doing some calculations, you can find out that the specific impulse that such an engine could reach would be about 1 million seconds. Multiply that by approximately 10 to get it to the right units of meters per second, and you would get an exhaust velocity of 10 millions meter per second. That's 100,000 kilometers per second, or about a third of the speed of light. However, as I just mentioned, this is still a theoretical system, as we are still testing the engineering feasibility of a terrestrial power generation fusion system, which is currently at the demonstration stage in the joint European Torus, the JET. This picture is a simplification of a steady-state fusion propulsion system. As you can see, a reaction chamber is surrounded by magnets which allow the deuterium and helium-3 or tritium fuel to be reacted at extremely high temperatures, close to 1 billion degrees Kelvin. Hydrogen is then injected at the exhaust of this reaction chamber and ejected out of the engine through magnetic field lines. Eventually, this creates enormous amounts of specific impulse or exhaust velocity and consequently enormous amount of thrust. Let's now have a look at nuclear fusion rockets using pulse propulsion. So, differently to the system that we just saw, using steady-state propulsion, pulse propulsion works more like a cannon, where you detonate charges that propel the rockets through pulses. As you can see on the image on the right, such a system would consist in a payload and a pulse unit storage containing the pulses to be detonated, separated by a momentum conditioner, which is essentially a big damper to absorb shocks and distribute them to the main structure, and finally a pusher plate which would receive the energy from the exploding pulse units. Another way to do it is to still have that payload and pulse unit storage system, but instead of detonating the pulses against a pusher plate, we detonate them in an explosion chamber. The gases and energy created is then channeled through an exhaust nozzle, which creates a system that is propelled similarly to an actual rocket. These systems can actually utilize a variety of light elements. There was a concept study called the Project Orion, started in 1955, that studied the possibility of detonating 1 megaton fusion bombs at the focus of a 1 kilometer copper reflector. I don't know if you realize, guys, what a 1 kilometer copper reflector would look like and weigh. So the copper reflector, sorry, is essentially the pusher plate, and that would be so enormous that there's no way we could take it from Earth and put it in space. This kind of spacecraft would be so huge that it would have to be built directly in space. So these systems have actually been tested at model scale with conventional explosives like TNT or other plastic explosives. And it really does look like it could work at a proper scale. Another project that looks at using nuclear fusion pulse rockets for interstellar travel is Project Daedalus. Project Daedalus is a feasibility study of sending an unmanned probe, essentially a drone, to the nearest stars. It plans to use pulsed fusion of deuterium helium-3 or tritium pellets, which are ignited by high-power lasers electron beams. So it's a similar ignition system and fuel that we have seen in the steady-state propulsion system. The greatest challenge actually lies in the 40-year-long flight reliability, which requires self-repair systems and AI capabilities way beyond what is presently feasible. So essentially, the propulsion systems are actually doable with today's technologies. I mean, the pulses are essentially fusion atomic bombs, which the US, France, and other countries currently have in stock. We also are able to build structures that would sustain the loads and the speeds involved in such a spacecraft. The one thing that we cannot do yet is that, like any engineering system in our imperfect world, materials would decay, tiny collisions would happen in space, and defects would occur. So this spacecraft on such a long journey of 40 years would obviously need to be repaired and maintained at some point, like any vehicle. Obviously, if it's unmanned, who is going to do this? So the point is to develop artificial intelligence and systems that are able to repair themselves so that the spacecraft can carry up that journey for that long. I personally think that within our century, all these systems will be built, particularly with the advent of quantum computing and new materials, organic composites that are able to repair themselves. If you combine the two, you should get something that can last years and years of running at extreme velocities and in extreme engineering conditions and still make it. Let's now look at the actual mission of Project Daedalus, which is expected to go to Barnard Star. Barnard Star is located 5.9 light years away from Earth. So light takes 5.9 years to reach that star when it leaves our planet. The departure mass of the Project Daedalus spacecraft would be 50,000 tons, 50 million kilograms, distributed over 2 stages. Deuterium and tritium fusion would be triggered by electron beams, as we just saw. The expected terminal velocity of the spacecraft itself would be about 12% the speed of light, or 36,000 kilometers per second. At these speeds, what's interesting is that you start having some relativistic effects, where actually time for the spacecraft itself passes more slowly than for us. So if you were on board the spacecraft, let's say if your 1 year passes, then time for people on Earth would actually have passed more slowly, like a bit more than a year. The closer you get to the speed of light, the worse that effect gets. And interestingly enough, as a little parenthesis, the most extreme condition of this property is when you get inside a black hole. if you were to pass through the event horizon of a black hole and look behind, you would actually see the whole universe die before you would finish entering the black hole. And that's because time would slow down progressively for you until it completely stops at the event horizon. What that means is that as you look back, you would see the universe aging faster and faster and faster as time for the universe would pass a lot faster than for you. So this project is currently being updated as Project Icarus in order to potentially investigate the thousands of recently discovered exoplanets, notably thanks to the Kepler spacecraft. Let's now look at something even crazier. Nuclear fusion implemented through a Bussard Ramjet. So it is theoretically possible to create an interstellar vehicle capable of traveling without carrying its own propellant mass or energy supply. Space is not perfectly empty. It is made of atoms in a density of about 1000 atoms per centimeters cubed. It sounds like something, but it really is nothing. I mean, on Earth, there's billions and billions of atoms in a single cubic centimeters if you're at the sea level. So what you can do is if you go sufficiently fast, if that medium is suitably collected, confined, and compressed by a magnetic field configuration, then fusion ignition temperatures could be reached. And this is similar to an atmospheric ramjet, and it would need to reach a critical speed of about 10% the speed of light before the engine is self-sustaining. So imagine that you start by using a pulse propulsion system. Using that pulse propulsion system, you eventually reach a velocity of 12% the speed of light. Now, that spacecraft also has a Bussard Ramjet. So you shut down the pulse propulsion and you can now use the ramjet, which compresses the ions and atoms that are spread about in space in such a tight space and at high temperatures that these atoms actually fuse together, releasing enormous amounts of energy and exhausting at the back of the spacecraft, creating thrust and propelling it at a sustainable 10% the speed of light. This concludes our lecture on using nuclear fusion in rocket propulsion systems. I hope you guys enjoyed it. I particularly did. This is a subject I'm passionate about. I think it's the future. All these ways of propelling ourselves to incredible velocities, much faster than what we achieve today, is what will allow us to reach and discover new stars, new planets, and potentially extraterrestrial life. As usual, if you have any questions, guys, do not hesitate to message me or contact me. Thank you.